For the problem segment, there are three major concerns that we consider, including efficiency and heat output, durability and reliability, and lastly, user-friendliness. There are three objectives for this project. The first one is develop a waste cooking oil stove design that utilizes waste cooking oil as a renewable and sustainable fuel source. Second, develop a stove that can effectively burn waste cooking oil by addressing issues including fuel supply, burner design, and heat transfer mechanisms. Third, assessing the practicality and effectiveness of the Stirling Engine system for converting waste heat to mechanical energy, taking into account variables such as power output, mechanical energy conversion efficiency, and overall system performance. The scope of the project involves first, design and implementation of a waste cooking stove. Second, performance evaluation of the stove. Third, heat generation and blower speed. Fourth, fuel consumption and blower speed. Fifth, boiling rate and blower speed. Sixth, Stirling engine voltage output.
Now, we will go through the methodology. For methodology, we have 4 phases that need to be done, which is first, initial study. For this phase, we do some literature survey and visit, and also preliminary practical analysis. For the second phase, which is computational design, this is where we design the whole system using CATIA software. Third phase is the physical development phase, where we fabricate the system. Lastly, fourth phase is where we do experimental and analysis. Also here, it shows that the electrical part of the system that we have designed using Tinkercad. And from the table, we can see the voltage being consumed and produced from each electrical component. Next, for concept description, this is the front view, side view, top view, and isometric view that we have designed using CATIA software. Next, here it shows how we collect data for the experiment. From the first picture, it shows how to get the temperature from the stove that has been fabricated using thermocouple. As for the second picture, this is how to get the temperature of the water using thermocouple. After that, the third picture shows how to get the mass of waste cooking oil during burning process using scale. Lastly, it shows how to get the voltage that has been produced from the Stirling engine using multimeter. Next, this is the product that we have fabricated from the CATIA design and Tinkercad. Here, we can see the cooking oil container used to store the waste cooking oil, capillary tube pipe to keep the oil flow to the burning chamber, blower casing and DC motor, we provide air into the burning chamber to help the burning process. As for the electrical part, we can see the Stirling engine being used to generate electricity as the heat from the chamber being supplied to it. And lastly, for potentiometer, it is being used to control DC motor speed.
Okay, this is the demonstration of our product or model prototype. Okay, first we allow the waste cooking oil to flow into the burning chamber by opening the pipe. Then, to light the waste cooking oil, we insert some burning tissue into the burning chamber. We connect the circuit to the battery to power the blower. Then we have to wait for a few minutes for the Stirling engine to start. After that, we control the blower flow via a potentiometer, which has 3 settings: no blower, 50% blower, and 100% blower. Lastly, we record the data using multimeter, thermocouple, and scale. Here, we also attach the demonstration video of our product or model prototype. Okay, these are the 3 blower settings, which are controlled by the potentiometer. Okay, for the first setting, which is the no blower, it uses 2 volt from the supply, which are the battery and the Stirling engine. And for the second setting, 50% blower, it uses 3.1 volt. And for the last setting, 100% blower, it uses 4.3 volt from the supply. Okay, next is the result and discussion from our project experiment. Okay, for the first one is the temperature produced from the stove. Okay, we measure the fire temperature produced by the stove in degrees Celsius. We record them using thermocouple. The conditions are differs by the 3 different blower settings. Okay, for the first blower setting, which is the no blower, it generated the fire temperature of 305 degrees Celsius. Then, for the second setting, 50% blower, it generated the fire temperature of 546 degrees Celsius. And lastly, for the 100% blower setting, it generated the fire temperature of 833 degrees Celsius. As you can see from the graph, the line of the graph increasing proportionally as the blower fan speed increase, the fire temperature also increase. Okay, next is the time water to reach 100 degrees Celsius. We measure the time required for pipe water to reach 100 degrees Celsius. We record them using stopwatch and thermocouple. We also use 3 different blower speed settings for this experiment. We control 2 constant values for the rest of the experiment. The first one is the mass of water of 325 grams and the initial water temperature of 32 degrees Celsius. Okay, for the first blower setting, which is the no blower, the boiling time is 22 minutes. For the second blower setting, 50% of the blower, the boiling time is 3 minutes. And for the last blower setting, which is the 100% of the blower, the boiling time is 2 minutes. As you can see from the graph, as the blower fan speed increase, the boiling time decrease.
Next, for the result and discussion is the mass of waste cooking oil during burning process. The experiment was done in 30 minutes duration and the mass is recorded using scale. As the blower speed increased, it results in increasing of the airflow, combustion and also the heat output. And more waste cooking oil required to meet the demand. As you can see here, when there is no blower, the value of fuel burn is 75 gram, while 50% of blower is 125 gram and 100% of blower is 150 gram. As you can see in the graph there, as the blower speed increase, the value of fuel burn is also increased. Next is the voltage produced in 30 minutes with load by Stirling Engine unit with step-up booster and the support from 9V battery. The load that's been mentioned is the motor, step-up and LED. The motor required 6V while step-up required the input of 2 till 25V and LED required about 1.8 till 2.5V. As you can see here, the experiment was done in 30 minutes and during this 30 minutes, the voltage produced is maintained around 3.6 till 3.68V.